All right, welcome back. And so this Sunday would be the deadline of assignment one, and it is a firm deadline. Means if you if you miss it, you will get 0 mark for the assignment one. So make sure you have submitted your answer sheet before the deadline. The deadline would be around 9 p.m. on in Sunday. So here is a typo. It's not Wednesday. It's 2nd of August. So it's this Sunday. All right. So for the assignment questions, here I'm gonna trying to clarify a few things, as I've seen questions and discussions in PIADA for the last past couple of weeks. First question is about HDFS. Here, when we say R be the total number of blocks, there are indeed two different interpretations of this R, and where one is to take R as the total number of blocks, and the other is to take R as the total number of block replicates, which means for the first interpretation, the total number of block replicates would be R times 5. 5 is the replication factor. So we will take both interpretation as correct in this question, because although they will lead to different answers, but it will not affect your understanding of this problem or of this topic. So we do accept both interpretations, just to make sure you have stated them clearly. And for the first one, you need to write down the formula of LIKN, where LIKN is the number of blocks that have lost I replicates. And for the second question, here we said that you need to show both the steps and the final results. For the steps, if you are using a Python code, for example, you can copy and paste your code on the PDF, or if you are using or you can write down the pseudocode you are using. That is fine too. Some students might use Excel to do the computation. Then you need to write down the Excel formulas. I don't think there would be students who do it by hand, but in that case, you need to show your steps as well. Here, the purpose of asking you to show the steps is to make sure that you have done this by yourself and you do understand the solution. All right. So it is better to let you just show the final result. For the second question about Spark, here the second question 2.2, where we ask you to list all the stages in the above code. Students were asking about like what format do we expect it? Do we expect? So basically, you can write in any format as long as it is clearly shows your understanding of what is a stage, and we're not expecting to to see identical, like exactly the same way of presenting a stage, but as long as your understanding is correct, you will get full mark for this question. For the third one, what makes the above implementation inefficient, and how would you modify the code and improve the performance? It is a open question, so the answer is not unique. But we do expect some, like let's say, basic or fundamental answers for this question. So if you are not pointing, if you are not pointed that out, then you may lose some marks. So this basic answers or naive answers, yeah, naive answers would be a better word here. So this naive answers is really naive. So it is obvious enough for you to figure that out. All right. So that's for the second question. The third question is about LSH, where the first sub question is asking about how many tables do we need. So it is essentially the L here, which is the small l in the lecture notes. So we have defined the definition of a near duplicate if the cosine theta is no less than 0.9. And here we want to know that how many tables do we need to ensure that we can find any we can find any near duplicates with probability of no less than 99%. And the second sub-question, here we consider an image O with cosine theta smaller than 0.8, and the K and L are given. So we want to know the maximum value of the probability of O to become a false positive of the query queue. So false positive means O is incorrectly returned. Since the cosine theta is for image O, the cosine theta is smaller than 0.8, then as long as O is returned, it is a false positive. All right. So I've seen some discussions in PIADA that kind of make this question complicated, which you might not have to do that. All right. These two questions are not that complicated. And also you need to show the intermediate steps along with the final result to get full credit. Also, don't forget to include your name and student ID on the first page of your submission. And we do not accept handwritten answers, so you make sure you type them in the text or in Microsoft Word or in Pages or whatever. I mean, anyway, you need to convert it into a PDF, and the size of the PDF should not be very large. We do have a size limit in the Give system, and it is not easy for us to change it because we do have limited storage in the machine as well. So the last thing is we don't accept late submissions, so make sure you submit your work on time. All right, so that's pretty much all for the assignment. All I need to say about the assignment before the submission deadline. And good luck for the assignment. Now let's come back to the lecture contents, which is sliding windows problem in data stream. So let's recall the problem. So we're given a stream of zeros and ones, so it's a stream of bits. You can think like that. We want to know that how many ones are in the last k bits. And here we are. I think we were here before. All right. So this algorithm actually solves the problem of, it can be used to solve the problem of like how many ones are in the last k bits out of where k is smaller than n. But let's start to thinking about a simplified version of this problem, which is that we want to know the number of ones in the last n bits. So n is a fixed number. We will show how to convert the problem into a more flexible version later. Right. So we were here on Monday when we stopped. The idea of this algorithm is that instead of summarizing fixed length blocks, we summarize blocks with a specific number of ones. And we let the block size, which corresponds to the number of ones, increase exponentially. Exponentially means you start from the block size of 1, then 2 and 4, 8, 16, and so on and so forth. So each one is 2 to the power of r, where r is from 1 to 2 and so on. And the good thing about this is that when there are few ones in the window means okay, this window of size n, then you can expect the block size stays small because for example, in the extreme case, there is only one bit that is 1 in this block in this window. Then we only need one block with size 1 to represent it, right? So the errors are really small. Right. So now the thing is that if we're using such kind of schema, what we need to do is that we need to recover or estimate the number of ones in this window, right? And we also need to change the answer when there are more bits coming in. So we want to be able to make the estimation at any time, right? At any time. So in order to do that, we need to store two kinds of informations. One is a time step, and the other is the bits. For time step, we need to know, for example, we need to know when we can through these buckets or block. So when we can through this block, for example, if we know that current window, the leftmost side of the current window is here, so we can through this window, this block away, right? In order to do that, we need to know a time step, so that we can know whether we can through or not a particular block, right? So the time step is used here, and the bits is the bits is used to do the to make the estimation, right? And for the bits, we only care about ones, so we don't need to do anything for the zeros. Right? And you can imagine if we were asking about the number of zeros, then you can just replace the ones here with zeros, then you can answer that kind of question as well. So they are basically equivalent. For the solution, you use the same solution. Right. So for time steps, now each bit in the stream has a time step. It's starting from 1 and then 2 and 3, so on and so forth. So this starting from is the beginning of the stream. It is the beginning of the stream. And so you can imagine each time when a new bit comes in, we can assign it with a new time step. Right? But we only need to record time steps module n, where n is the window size. So we can represent any relevant time step in big O of log n bits. Here the idea is that because we only care about last n bits, right? So for those old bits that are not belongs to the last n bits, we don't care about their time steps anymore. So it is meaningless to store a large number because the size of the data stream could be very large, but you don't need to store a large number for the new bits. You just need to store to represent that bit, or to represent the timestamp of that bit using a number that is smaller than n, right? As long as we have, as long as for the bits in the window we have different time steps, and they have a particular order. Right. For example, in this example, let's say the current n is from here to here, right? And yeah, here we have 11. Let's say n equals to 12. Right. Then let's assume that this one is with the time step of 1 and 2 and 3. So this one would be 12 mod n, which is 0. Right. Then when a new bit comes in, the window would move 1 bit to the left. So the new window would be like this. Right. So in this case, this bit, the timestamp is still 2. But for the new bit here, the timestamp is 1. Right. This one is 0 as well. So you can guarantee that there are timestamps from 0 to n-1 in the window of size n at any time. And they do have a particular order. For example, you know that the rightmost bit has the timestamp of 1, then you can expect the rightmost bit, the timestamp would be 1 plus 1, which is 2, and so on and so forth. So in this case, we make sure that the timestamps are always smaller than n. Are always smaller than n. Then we can use log 2n bits to represent an integer that is smaller than n. Right. This is the fundamental thing in computer science. All right. So for example, given the window size of 40, which is n, the time step 123 will be recorded as 3 because 123 mod 40 equals to 3, and thus the encoding is on 3 rather than 123. All right, so this is how we represent a time step. Right, how we represent a time step, and just remember, all we need is log n bits to represent a time step. Now let's look at the buckets, and also how many bits do we need to represent a bucket. So a bucket in the DGIM method is a record consisting of the time step, right, and the number of ones. So a bucket is equivalent to a block, where we have mentioned before in this algorithm. Right. So for each block, we need to maintain the time step of its end. For example, the time step of this and this, and so on and so forth. Right. And these time steps, we only need a big O of log n bits. We also need to record the number of ones between its beginning and end. So we do have the additional constraints on the buckets that the number of ones must be a power of 2. So the number of ones could be a power of 2, like 2 to the power of r. Right? So in this case, how do we in this case, how do we store the number of ones? Right? Because we know the number of ones must be a power of 2, then instead of store the number of ones, we can only store the r here. And we also know that r is of big O of log n, because the maximum number of ones in a block or in a bucket with given the window size is n would be n. Right? So for in this window, there will be no more than n ones in this window or in a bucket. So this r, so because we know that 2 to the power of r is smaller than n, so it means r is smaller than log n, so which makes it big O of log n. So we only need to store this r, and in order to store this r, we need a log of r bits, right, which makes it a log of log n bits. So this is how we get this big O of log n bits. Right. So for each bucket or each block, we need we need log n bits to store its time step, and log n bits to store the number of ones in that bucket. So this is how we store or represent a bucket with very few bits. So it is like a compression, right? So you use fewer bits to represent a bucket, then you can save the space and answer the question like how many ones in a window size of n with a larger n. Right. Now let's see how do we represent a stream by buckets. Previously we only have the representation of the buckets. Here I probably should give an example about that. So let's say we take this as an example. So for the time step, we need to record the time step of its end, which is here. Let's assume that this one, the time step, let's say it is 18. All right. So in order to represent 18, we need to convert it into binary form, which is 10010. Yeah. So we need 5 bits for this one, and we also need to record how many ones in this bucket. So it would be 1, 2, 3, 4, 8 ones, which is 2 to the power of 3. So instead of storing 8, we're storing 3. Yeah, we're going to store 3, and 3 is 1, 1. The binary form is 1, 1. So we only need 7 bits to represent this bucket. But empirically, we cannot only just 7 bits here, because because as you would see later, we don't know if we just concatenate them together, we don't know where to split them up. So an easy way of doing this, it may not be the most efficient way, is to given a fixed number of bits for all the buckets, in this stream. Sorry, in this window. All right. So in that case, we need to know, for example, we need 5 bits for this one, for the time step. But in order to store any time step, we may need, say, 7 bits. So this is because n is smaller or equal to 2 to the power of 7. In that case, we would add 2 zeros at to the right of this binary form of 18, make it 7 bits. And also for this is the same. So we need log n bits. So we assume that log n would be, we know that log n is 7, as we can see here. So log n would be 3. So we would add additional 0 to the right of this 1, 1, make it 3 bits. So in this case, we need 10 bits for all the, also say for any of the buckets in the stream when we're using this method. All right, so let's look at how do we represent a stream by buckets. We firstly initial some rules. Right. First of all, the right end of a bucket is always a position with a 1. Well, since we only care about ones in the window or in the stream, the left side, or the left end of a bucket is always a position with a 1 as well, as you can see in previous examples. Right? And every position with a 1 is in some bucket. If it is not in this bucket, then it will be in that bucket. But we don't care about 0. Some zeros can be in a bucket, but some of them can be out of a bucket, as you can see here. Right? And either 1 or 2 buckets with the same power of 2 number of ones. Let's say if we consider buckets with, let's say, 2 to the power of r ones, then this kind of buckets, the maximum number of buckets with 2 to the power of r ones would be 2, and the minimum number would be 1. Well, actually here is not very accurate. We would explain it later after we finish all the rules here. So buckets do not overlap in time steps. You would see each and every buckets are separated from each other. And buckets are sorted by size. So earlier buckets are not smaller than later buckets. So earlier buckets are those buckets on the left. And the later buckets, since the new buckets in our figures, it should be on the right. And so if we combine this rule and this rule, then a more accurate description would be if, say, the largest bucket, where by largest we mean it contains the most ones. If the largest bucket has the size of 2 to the power of r ones, then for 2 to the power for the buckets with 2 to the power of r minus 1 ones, 2 to the power of r minus 2 ones, and so on and so forth, until it has 1, it has 2, and has 1, 1. For all these buckets, the number should be either 1 or 2. But since this is the largest bucket, the bucket with largest size in the window, there will not be a bucket with 2 to the power of r plus 1 bits. R plus 1 ones. Right, so this one does not exist. So this rule, when we say either 1 or 2 buckets, we actually means those with r that is smaller or equal to the largest one. The largest r in this window. Right. Now the buckets disappear when their end time is larger than n time until n time units in the past. Basically, the idea is that if this bucket is out of the window, say the window's here, originally the bucket is like here, and when the window comes to here, then this bucket can be disappeared or discarded. So that is the idea. Let's use an example to explain this. So this is the size, the window n, from here to here, and each box represents a bucket. And as you can see, the number of ones in the bucket are always a number of power of 2 number. Right? It is 1, 2, 4, 8, and 16, so on and so forth. Let's look at the previous slides and go through each and every rules. The right end of a bucket is always 1, right? And the left side, the left end are the same. So a bucket starts with a 1 and ends with a 1. Every position with a 1 is in some bucket. As you can see, all the ones are in a bucket. Either 1 or 2 buckets with the same power of 2 number of ones. For size 1, we have 2. For size 2, we have 1. Size 4, we have 2. Size 8, have 2. Size 16, we have 1. Right. And buckets do not overlap. As you can see, buckets are sorted by size. So larger buckets on the left side, small buckets on the right side. And finally, buckets disappear when their end time is larger than n time units in the past. We will see this later. So the reason that we have this number of rules, they serve two purposes. Right. One is for the updating of the buckets, and the other is for the estimation. Now let's look at each of them. So for updating the buckets, when a new bit comes in, just remember each time we will only have one bit comes in, we drop the last bucket if its end time is prior to n time units before the current time. So when the new bit comes in, the last n bits or the window will slide to the left, slide to the right for 1 bit, and it is possible that the last bucket or the oldest bucket or the leftmost bucket is out of the window. If that happens, we will drop it. And for the new bit, So this is in two cases for the new bit. It is either 0 or 1. It is either 0 or 1. If the current bit is 0, then you don't need to do anything because we don't care about 0, right? We only want to count how many ones in the window. We don't care about 0. So when a 0 bit comes in, the only thing we would do possibly is to drop the last bucket. But when when the coming bit is 1, then we will create a new bucket of size 1. And this new bucket only contains this new bit. So we create a new bucket for this new bit. And this new bucket, the time step is the current time. Or more specifically, it is the current time mod n, right? Now, if you still remember, I believe you must remember, we can have either 1 or 2 buckets with the same power of 2 number of ones. So if we have 3 buckets of size 1, then we need to reduce it, right? 3 is larger than 2. What we do is we combine the oldest 2, means the rightmost 2 buckets of size 1 into a bucket of size 2. So in this case, we would have a new bucket of size 2 and lose 2 buckets with size 1. Since we have a new bucket with size 2, then it is possible that there are now 3 buckets of size 2. If that happens, we combine the oldest 2 into a bucket of size 4. Then we have only 1 bucket with size 2 and a new bucket with size 2 with size 4, and so on and so forth, because in this case you may have 3 buckets of size 4, but when to stop? Because we have either 1 or 2 buckets with the same size. Let's say we only have one bucket of size 2. So after we create a new bucket of size 2, the number of buckets of size 4, after we create a new bucket with size 4, we now have 2 buckets with size 4, and it is under the rule. So we do not need to create new buckets or combine the old buckets. Combine the buckets into new buckets. We don't need to do that. So this is what we do if the current bit is 1. Now let's look at the example, which would be easier to understand. So the current state of the stream, we have this is the window. Actually, this is the window. I mean, all the bits you can see are in the window, and the window also contains all the bits you can see. Sorry, the window only contains all the bits you can see. Right. So now a bit of value 1 arrives, right? Because if a bit of value 0 arrives, we do nothing, except we might drop the oldest or leftmost bucket. Right. So the example is about a bit of value 1 arrives. Then we create a new bucket for the new bit. In this case, we would have 3 buckets with size 1. So what we do, we combine these 2 buckets to a new bucket. So this new bucket contains 4 bits here. in this case, we have one bucket with size 1, two buckets with size 2. But for this combination, so if you still remember, for each bucket, we record two things. One is the time step, and one is the number of ones, which we only store the power of 2 number, right? So in this case, we have, let's say this is T1, this is T2, or more specifically, T2 equals to T1 plus 2 mod n, right? So the R would be 0. So for this two blocks, it's like T1 0, sorry, and T2 0. This is a block. Now we combine them to a new bucket, and for this new bucket, we also only need to record the time step, which is the rightmost one. So it is T2, and the number of ones, which is 2. 2 is to the power of is 2 to the power of 1. So we just record T21. Or this one actually comes from you just need to use 0 plus 1, so you get this one. So the reason that I explain this here is to tell you that it does not matter how many zeros are there in between of these two blocks, right? Because as you can see, actually you can compute it through using T2 minus T1, but it really doesn't matter when you do the combination. Right? You don't need to count the number of zeros or whatever. Now, a new bit 1 arrives. We create a new bucket for it, right? And 0 comes, we do nothing. And then a new 1 comes, we create a bucket for it as well. Right now we have 3 buckets with size 1. We merge the oldest 2 into this new one. Right. Now we have 3 buckets with size 2. We merge the oldest 2, create this one. Right. So it's a bucket of size 4. And we have we have 3 buckets with size 4. We combine the oldest 2 to get a new bucket with size 8. And we have 3 buckets with size 8. We combine the oldest 2, get a new bucket with size 16. Right. And we have 2 buckets with size 16. We can stop. So this is what we do when updating the buckets or when the new bits comes in. Right. Then the next question would be how to query. We now know how to store the buckets or store the buckets in the window. We know how to update the buckets when the new bits comes in. And the left question would be how to query or how to estimate the number of ones in the most recent n bits. So the querying is actually easy. We firstly sum the sizes of all buckets but the last. The last means the rightmost. The leftmost. The oldest. And size here means the number of ones in the bucket. So we sum the sizes of all the buckets except the last one or the leftmost one. And we add half the size of the last bucket, then we get our estimation. Let's look at the example first. So this is the window n from here to here. So the estimation would be this is 2 times 1. This is 1 times 2, 2 times 4, 2 times 8. So for the first step, we sum the sizes of all buckets but the last. What we will have here is 28. Right, 28. So we have 28 ones from here to here. And we add half the size of the last bucket, which is 8. Then we will get 36, which is our estimation of the number of ones in the most recent n bits. And the reason that we add half the size of the last bucket is that we do not know how many ones of the last bucket that are still within the wanted window, because the window, right? The window only the bucket only has part of it in the window. Right? That's why we cannot get the exact number of how many ones are in this part. Right? So what we can do is to estimate it using half the size of this bucket. So if you still remember, we have claimed that the error is at most 50%. Now let's see why it is the case. Now we suppose the last bucket has size of 2 to the power of r. Then because we assume that half of its size, half of its size are still within the window, which is 2 to the power of r divided by 2 equals to 2 to the power of r minus 1, we make an error of at most 2 to the power of r minus 1. Because the extreme case would be there is only one within the window, or there are 2 to the power of r minus 1 in the window. In either case, I mean, the error is at most 2 to the power of r minus 1. Now let's look at the number of true sum. Since there is at least one bucket for each of the sizes that is less than 2 to the power of r, the true sum is at least you use 1 plus 2 plus 4 and so on and so forth until plus 2 to the power of r minus 1. What you will have is 2 to the power of r minus 1. So this is like the smallest possible number of ones in the of the true sum. Right. Actually, we need to plus 1 here because the rightmost bit of this last bucket must be 1, and it since it is in the window, right, so this one would be in the window, so this should be 2 to the power of 2 to the power of r. This is the minimal possible number of the true sum. Then what we have is this is the error and this is the true sum, so it is 50%. This is the 50%. And we know that the error is smaller or equals to this. And we know that the true sum is larger or equals to this. Which means if you use error divided by sum, it should be smaller or equals to this value, which equals to 50%. Therefore, the error is at most 50%.